Hey, good day, everybody. And today we have a nice, short, little, easy topic. And this topic we're going to be talking about distance and speed time graphs. So, what are they? They are just as you would expect. A distance time graph is just basically a graph in which you always have the y-axis to be distance, and you'll always have the x-axis being time. And with these graphs here, we would usually find that time would be on the x-axis. Okay? Now we could see here that this graph shows a journey that is illustrated in this question over here. A man left home to go to the grocery store. His journey is shown on this distance time graph. So we could take this point here, the origin, to be when he left home. So at this point, then no time has passed and no distance, so he didn't go anywhere yet. So we could see here that as time goes by, in half an hour, because we could see here that this time, this little h here, tells us time is measured in hours, right? So in this case, in half an hour, he got to the grocery store being 50 kilometers away, right? So we could see here that in that half hour to 2 hours, so this journey here took half hour to reach to the grocery store, and then from the half hour mark to the 2 hour mark, so this would be 1.5 hours here, it would have taken him inside the grocery store. Now, how did I know he was inside the grocery store? Well, he didn't travel any distance. Yeah, he parked at the grocery store, and we could see here that for that entire time, he stayed at that 50-kilometer mark, which means that no distance was traveled. And then after the 2 hour mark now is when he decided to go back home. So we could see the distance getting closer and closer to home until it goes back to 0, which is when it reached back by his house, right? So from the 2 hour mark to 2.25 mark, we could see that it takes him about 15 minutes or a quarter of an hour to get back home. Yeah. Now we could get a lot of information from this. Yeah. We could tell that it took him half an hour to get from home to the grocery store, but it only took him 15 minutes to get from the grocery store to home, which means that his journey home, he must have driven a lot faster, you know? So he drove faster to get home, yeah? So we could also tell how fast he drove because of how steep this line is. So we could tell that how steep this line is, and this line over here going to the grocery is not as steep. So depending on how steep this line is, this line would show his speed. So this line, we could find his speed, and we could see that he's traveling at what we call a uniform speed, right? Because it's a constant speed as he is traveling from home to the grocery store in half hour, right? He also drove at a uniform constant speed coming home simply because, and we know it's a constant uniform speed because the line is straight. Yeah? If the line was a curve like this, then distance and time, then that would show that his speed is constantly changing. Over here, he would have probably braked or was in traffic because he didn't travel much of a distance, and then he sped up here, and then over here he was in traffic again. So, you know, if you have a change of speed, you would end up getting a very curvy graph. Thankfully for CSEC, we don't have to deal with curvy graphs. So basically, all of our speeds are going to be uniform, straight line. So let's carry on with the question. How long did the entire journey take? Well, we can answer that from just looking at the graph here. We saw that from 0 hours, he took half an hour to get there, spent an hour and a half, and was back in 15 minutes. So the entire time took 2¼ hours. So number one, it took 2¼ hours. That's how long the entire journey took, right? How much time did he spend at the grocery store? Well, we already saw that he got to the grocery store at the ½ hour mark. He left the grocery store at the 2 hour mark. So that means he would have spent an hour and a half at the grocery store. So 1½ hours. 3. What is the total distance traveled to and from the grocery store? Well, to the grocery store, we could see that from home to the grocery store is 50 kilometers. And then from the grocery store back to home is another 50 kilometers. So the total distance he would have traveled to that grocery store would have been 100 kilometers. And that would have been to and from the grocery. Total distance traveled. Yeah. How fast or the speed did he drive to go to the grocery? So we saw here that he traveled at a uniform speed because of the fact that it's a straight line, right? So he's covering the same amount of distance in an equal amount of time. Yeah. So now we have to actually calculate what that speed is. And we can see here that we just need to know one simple formula. And the formula is speed equals distance moved over the time taken. Yeah. So in this case, and the distance moved was 50 kilometers. And the time taken was ½ an hour. So what we saw here is 50 divided by a half gives us 100, and we use these units here for speed. Kilometers and hours, 100 kilometers per hour. Yeah. Another way to write it, and you will see some people writing it as 100 kilometers per hour to the -1. So the h to the -1, it's just a fraction thing, and they both mean the same thing. So we could see here for number 4 that he drove 100 kilometers per hour, right? So how fast did he drive returning from the grocery store? Well, we could see from the graph that he took a less amount of time, which means he drove faster. So let's see exactly how much faster he drove. So speed is equal to distance moved over time taken. So that would have been the distance moved is the same 50 kilometers coming back from the grocery store. But the time taken would have been 15 minutes or a quarter of an hour. So coming back from the grocery store, 50 divided by a quarter actually gives us, wow, 200 kilometers per hour. So we could see that coming back home, he was driving very, very fast, 200 kilometers per hour. And that's pretty much it for distance time graphs. We could see with a distance time graph that the y-axis, we're talking about distance, and the x-axis, we're talking about time, whether it's in hours or in seconds. And we can see here that from a distance time graph, we can also find out the speed, which is the distance moved over the time taken. Yeah. And that's pretty much it for distance time graph. And let's take a look at another type of graph. and that is our velocity time graph. Now, a velocity time graph is the same concept as a distance time graph. It's just that on the y-axis we now have velocity, and on the x-axis we still have time, and in this case time is in seconds. Yeah. Now, a velocity time graph, it basically shows us a velocity over time. So we could see here that if a car was traveling from a velocity of 0, and remember, what is velocity? Velocity, it's just another way of saying speed. The difference between both of these is that speed is a scalar quantity, so it only has magnitude, and velocity is a vector quantity, so it has magnitude and direction. And that's pretty much the difference between velocity and speed, but generally we could think about them as almost the same thing. So we could see from the graph here that he starts with a velocity of 0, and he increases that velocity, which means he's going faster and faster and faster until he reaches a maximum velocity of 50 meters per second. Yeah? He reaches 50 meters per second in this space here of 5 seconds here. Okay. Now we could tell that he is going from 0, and he is constantly rising in velocity until he reaches the maximum of 50. So that means that, halfway through he would have been at 25 kilometers an hour, and then maybe even 40 kilometers an hour. So we could see here by this sloped line that the velocity is constantly changing. It's constantly increasing. So what do we say when velocity is constantly increasing? The change in velocity, so when a velocity is changing, that is what we call acceleration. So we could see here that he is accelerating from 0 to 50 meters per second, right? So he's accelerating from 0 to 50 meters per second, and he takes 5 seconds to do so. So this slanted line on a velocity time graph, the slanted line gives us acceleration. And remember, because it's a straight line, means it's uniform acceleration. So the acceleration isn't changing. His velocity is changing at a constant rate. So when the velocity is changing at a constant rate, that is uniform acceleration. Now, of course, here we could see that he stays at that velocity. So at the velocity of 50 meters a second, he stays there for a further 10 seconds. So at 10 seconds, he travels here at a constant velocity. And please note, if we have a constant velocity, that means that there is no change in velocity. And if there is no change in velocity, that means that for a constant velocity, there will be no acceleration. Now we could see here that at the 15-second mark, after 10 seconds of staying at a constant velocity, he starts to slow down. And it takes him 3 seconds to slow down from 50 meters a second back to 0. So we call this, when you are slowing down, we call it deceleration. So we have acceleration, uniform acceleration, which means that he is increasing velocity at a constant rate of change of velocity. And then uniform deceleration means that he is just slowing down. So we can see here that for acceleration, we have a velocity time graph. The x-axis is time, the y-axis is velocity, so we can actually calculate the acceleration, and that is the change in velocity all over the time taken. So in this case, we could see that the change, he goes from 0 to 50. So for our acceleration, he goes from 0 to 50. So the change in velocity would be 50 minus 0. And he takes 5 seconds to do so. So that'll be 50 divided by 5, which is 10. Now remember, velocity, all right, acceleration is equal to velocity over time. Velocity is meters per second and time is in seconds. So acceleration will be in meters per second squared. Yeah. So just remember, these are units for acceleration and for velocity as well as distance. Now, in order to calculate distance, we could actually calculate the distance that he moved at the constant velocity. So he stayed at a constant velocity of 50 meters per second during this time, 10 seconds. Yeah. So what distance did he travel at that constant velocity? Well, the distance from a velocity time graph can be easily calculated by just finding the area under the graph. So the area of this section here will give us the distance that he traveled. We could see here that this is a rectangle where this side is 10 seconds and this side is 50 meters per second. So the area of that part of the graph would be 50 times 10, which is 500 meters. Yeah. We know meters because the velocity is in meters per second. So just by finding the area under a velocity time graph, we can calculate the distance. So let's check out a velocity time graph question. So a racing car starts from rest at a point A and travels with a uniform acceleration of 12 meters per second squared for 8 seconds. So they actually gave us the acceleration here, and we can remember that acceleration equals velocity over time. For the next 20 seconds, it travels at a constant speed and then brakes uniformly, which means he's slowing down, and that slowing down occurs for 12 seconds. So the first thing we have to do here is draw a speed time graph to represent the journey. So obviously now we'll have this axis being velocity, and our velocity will be in meters per second, and we will have this axis here, the x-axis, being time in seconds. Now at the end of the day, for the start of the journey, they did not give us the velocity. They told us he accelerated at 12 meters per second for 8 seconds. So we have the acceleration, we have the time, so now we could find the velocity. So the acceleration is 12 meters per second, and that is the velocity all over 8 seconds. So I'll just take the 8 and throw it across there. So now 8 times 12 will give us our velocity. And our velocity ends up being 96 meters per second. So we could tell that he reaches his maximum velocity at 96 meters per second. And now we could have an idea as to how to draw. So we have the point A over here where he starts, and he'll start at 0. He reaches 90, and let's mark this at 8 seconds. All right, 8 seconds. So we'll draw our line here, and this straight line represents our change in velocity, which is the uniform acceleration, right, for 8 seconds. Then they say that for the next 20 seconds, he travels at a constant speed. So he doesn't change this speed. So this speed remains constant for 20 seconds. So that means that this will be the 28-second mark here. So that the distance from here to here is 20 seconds. And then he takes 12 seconds to decelerate. So a further 12 seconds now, 28 plus 12, that'll put us at the 40-second mark. And that is where he decelerates. And of course, this period in time here is 12 seconds. And this would represent a rough sketch of our speed time graph or velocity time graph. Now, hence or otherwise, number 1, calculate the distance traveled during the first 8 seconds. Well, we know that to find distance in a velocity time graph, we need to find the area under the graph for the first 8 seconds. That'll be this area here. We could see that this base is 8. We could see that the height we could take at 96. And so that'll be the area of a triangle. So the distance equals a half base times the height, which is a half of 8 times 96. So that distance gives us 384 meters. Well, we know that the average speed for the entire journey, we saw that speed is distance all over time. So we want the average speed for the entire journey. We know the time it takes for the entire journey. The time is 40 seconds we saw here. The entire journey takes 40 seconds. So all we need is the distance he traveled for the entire journey, right? So that means that we need to find the area under the entire graph. Now we could see here that this graph is a trapezium. So the distance, total distance, will be the area of a trapezium, which is a half the sum of the parallel sides by the perpendicular height. And in this case, we could see that as a half, the sum of the parallel sides will one side, this underneath side here, will be 40. And this top side here will be 20. And we're reading that straight from the graph. So 40 plus 20, and that is being multiplied by the height, which is the 96. So that'll be a half into 60 times 96. Which is approximately 2,880 meters, right? So now that we've calculated the total distance, now we can calculate the average speed by saying that the average speed would be the total distance over the total time, which is 2880 divided by 40. So his average speed is roughly 72 meters per second. Remember, this is speed, not acceleration, right? Nice, and that's pretty much it for velocity time graphs. As we could see, it was a very, very easy topic. Not much, just a couple of things that we had to remember, and a couple of new formulas, that being speed is distance over time, and acceleration is velocity over time. So if you have any questions about this topic, feel free to ask in class or contact me anytime, and have a good day.